Hey everybody, welcome to topic 9.02, enthalpy. Last time we met, you learned about reaction mechanism, the steps that the reaction takes. You learned how to change the mechanism using catalysts and inhibitors, and how to change the reaction rate by changing temperature, concentration, pressure, or surface area. Last time we said that the collision causes old bonds to break, and energy gets absorbed during that collision. When new bonds form, energy is released. We're going to take a look at that energy today in a topic called enthalpy, which is just another word for potential energy, stored energy, and what's happening to it. So, to introduce this, let me introduce you to reference table I. This is reference table I. This is an extremely useful reference table, giving you all kinds of great information. First, on the top, you've got 6 combustion reactions. Combustion takes place when a carbon compound bonds with oxygen, forms carbon dioxide and water vapor. It's also going to release a lot of heat. We also call combustion burning. Okay. Then we have a series of reactions where elements are combining to form compounds. These are synthesis reactions. Some absorb heat, some release heat. If you want to get the amount of energy for a decomposition reaction, simply change the direction of the arrow. Go from the right to the left, and that will be decomposition. Then we have a series of reactions where we have H2O over some arrows. These are all dissolving or ionization reactions. These are actually physical changes, not chemical changes. You'll notice that the amount of heat involved is typically much smaller than for the chemical changes above. And finally, the very last is acid-base neutralization, where the hydrogen ion from an acid combines with an hydroxide ion from a base and produces water. So it's very useful information indeed, but that's not the most useful information here. There's extremely convenient information on the bottom. The delta H values are based on molar quantities represented in the equation. What that means is that this plus 66.4 here, that's for 2 moles of NO2 being formed. If you want to figure it out for each mole, you would just take that 66.4 and divide it by 2. That's what it means by the delta H values are based on molar quantities. And even more important, a minus sign indicates an exothermic reaction. So any of these that has a minus sign before the amount of heat absorbed or released, these are exothermic reactions, reactions that release energy. Anything with a positive change in heat will therefore be endothermic. Oh yeah, remember that? That was a while ago, wasn't it? Or it could have been like 5 seconds ago if that's the last video you watched. So what is this delta H thing anyway? Well, it's either the heat that's absorbed, which is the positive delta H, or released, the negative delta H, during any kind of change, whether it's physical or chemical. Now, according to this table, forming aluminum oxide from its elements releases, see that minus sign there, 3,351 kilojoules of potential energy. That's for every 2 moles of aluminum oxide formed. So if you decompose these 2 moles, if you go the other way, it will absorb 3,351 kilojoules. So all you have to do is reverse the sign when you reverse the reaction to find out how much energy is involved. Okay. Forming 2 moles of hydrogen iodide from its elements will, see positive right here, absorb 53.0 kilojoules of potential energy for every 2 moles of hydrogen iodide you formed. If you want to find out for 1 mole, you just simply take our 53 and divide it by 2. So decomposing 1 mole of hydrogen iodide, well, decomposing 2 will release 53.0 kilojoules of energy. Decomposing 2 moles will I'm sorry. Yeah. Okay. So that would be for 2 moles. So we want 1 mole. So we take that 53.0 and we divide it by 2. So each mole of HI will release 26.5 kilojoules of potential energy when it's decomposed. Ha. Okay. So how do we write this energy in reactions? Well, when you have an exothermic change, the heat is released as a product. And so for this reaction here, which has a negative delta H, if you want to put that energy into the reaction, you just simply write it as a product. Wait, it says negative here. How come you made it positive here? I didn't. Delta H is change in heat. The negative sign indicates that the change is negative. It's kind of like if I walk out of my house with $60 in my pocket and I come home with $40 in my pocket. My change in money is negative $20. I lost $20. Now, I didn't give away a negative $20 bill. It's that the change in money was negative 20 because I now have 20 less than I had when I started. So these reactants here had a certain amount of energy. 483.6 kilojoules of that energy was released. H2O, therefore, will have as much energy as it takes so that the total combined heat of the reactants equals the total combined heat of everything on the product side. So let's say the total combined stored energy here was, let's say, 500 kilojoules. Now, of that 500 kilojoules, 483.6 of them were released during the reaction, meaning the remaining, that would be 16.4 kilojoules, is left stored in the bonds of the water. So this is the total amount of heat that was lost, and we show that loss by putting the heat on the right side, the product side of our reaction. In an endothermic change, we put the heat on the left side. So in this reaction, the change in heat is plus 52.4, which means when we write the reaction, we put that heat on the left side of the reaction. I left the house with a certain amount of money. I found $52.40. So now when I come home, I'm going to have $52.40 more than I had when I left that morning. So let's say, for example, the combined heat of carbon and hydrogen is 20 kilojoules. By adding this many kilojoules, this is going to have a total heat of 72.4 kilojoules. I'm not saying that's how much heat's actually in here. I'm just pulling numbers out of my buttocks. Okay. Stability of the products, the ability to undergo a reaction. Exothermic changes have more energy stored to begin with than they have when the reaction is done. The reactants having more energy in them are more unstable, and by that I mean more likely to undergo a reaction. The heat of the products being lower means that the products are less likely to undergo a reaction. Therefore, we refer to them as stable. In an endothermic process, we have less energy to start with than we have to end with. So what that means is that our reactants are more stable, but our products are less stable. To give you an example of this, in an exothermic change, it's like burning. You have a lot of energy stored in your fuel, but over the course of the burning, that energy is released. Fire. And the resulting ashes that you're left with when the burning is over don't have enough energy left in them to burn anymore. So the fire goes out. So the reactants were unstable, but the products were stable. Imagine making dynamite. Whatever reactants you start with, they don't have a lot of energy stored in them, but when you combine them together, you pack a lot of energy into it. So the final result, your dynamite, has a lot of energy packed in it. It's very unstable. Now, potential energy diagrams and how that works. Potential energy diagrams map the potential energy of a reaction in the 3 stages of the amounts of energy that you can have during a reaction. First, we have reactants. That's what we start with. Those reactants have a certain amount of energy stored in their chemical bonds. This is the heat of the reactants. We add activation energy to break the old bonds. We have to add the energy to break the old bonds, right? The reactants have to collide with enough energy to break those old bonds. That's activation energy. What happens then is you have the activated complex, which is this soup of substance where the bonds have been broken and the new bonds haven't quite formed yet. It's sort of the middle stage. This has a certain amount of heat associated with it as well, the heat of the activated complex, the heat of what you have once you've managed to break all the bonds. Then, as new bonds form, energy is released and products are formed. And those products also have a certain amount of energy stored in them. In an exothermic reaction, we have more heat in the reactants than we have in the products. And in an endothermic reaction, we have more heat in the products than we have in the reactants. The difference between the heats of reactants and products, that is the heat of the reaction, the delta H. Delta H is defined as the heat of products minus the heat of the reactants. All right, let's see how that works in an actual graph. Okay, let's say that we start off with 80 kilojoules of energy stored in our reactants, and it takes 30 kilojoules of additional energy to break the old bonds. So we're going to put potential energy on the y-axis, and we're going to put time on the x-axis, but we're not going to call it time. We're going to call it reaction coordinate, which means from the beginning of the reaction to the end of the reaction. Because otherwise, if we put time here, we'd have to put like 0 seconds, 0.001 seconds, 0.002 seconds, 0.003. We're not going to do that. We can put units for potential energy, but this axis here will remain without units. It's basically just saying as the reaction proceeds from start to finish, what happens to the potential energy. We're not going to worry about how much time has gone by. Okay. Our reactants have 80 kilojoules of energy stored in their bonds, and in order to break those bonds, we have to add an additional 30 kilojoules of activation energy. When all the bonds have been broken, therefore, our activated complex will have 110 kilojoules of total energy, the amount of energy that makes it impossible for the bonds to remain. Then it says here that we release 60 kilojoules of energy. Now remember what we said is the total amount of heat on the left and the right have to add up to the same thing. If the heat of our reactants is 80 kilojoules, and we already have 60 kilojoules released, that means the heat of our products is what plus 60 gives us 80? Only 20 kilojoules of energy is left stored in our products, which means that 20 minus 80, the heat of our products minus the heat of our reactants, 20 minus 80 means a total heat of reaction of minus 60 kilojoules. To actually graph this, we start at reactants, we go to activated complex, and down to products. And this is what an exothermic potential energy diagram looks like. There are 80 kilojoules of energy stored in the bonds of the reactants. The reactant molecules collide with 30 kilojoules of energy. This gives those molecules enough energy to break the old bonds. This occurs at a total of 110 kilojoules of energy and is called the activated complex. The old bonds have now broken, and now new bonds begin to form, and these bonds form the product. The product has 60 kilojoules less energy stored than the reactants, and therefore only have 20 kilojoules of energy stored in them. And since heat of reaction is heat of products minus heat of reactants, 20 minus 80 is a negative 60 kilojoule total potential energy change. That's exothermic. Now let's look at endothermic. You'll notice a difference in the exothermic reaction. The heat was on the right side to show that it was released. But in the endothermic reaction, now the heat is on the left side of the arrow to show that it's been absorbed. That means the reactants are going to have 40 kilojoules less energy than the products do. The reactants have 40 kilojoules of total energy. That has nothing to do with each other. I just, again, pulled that number out of my buttocks. Anyway, so when we graph this, the reactants have 40 kilojoules of energy. We have to, activation energy is 100 kilojoules. We have to add 100 extra kilojoules, activation energy, to break the old bonds. Now, if we only added 50 kilojoules of energy, the molecules would collide with each other harder, but not hard enough to break the old bonds. We need at least 100 kilojoules. We have to bring the total energy up to 140 kilojoules before all the bonds break. When the bonds break, then new bonds will form. If it's exothermic, it will feel warm. Isn't that delightful? Anyway, so we bring it to 140 kilojoules. And at this point, all the bonds in the reactants that need to be broken for this reaction to happen are broken. Now, according to our reaction up here, if our heat of reactants is 40, and we're adding a total of 40 kilojoules to make the products, that means the products will have 40 kilojoules more heat than the reactants did. And if we add 40 to 40, we get, hard math, 80 kilojoules is the heat of our products. 40 plus 40 is 80, and that's the heat of our products. So we draw a curve. We start with reactants. We add 100 kilojoules of activation energy to break the old bonds. The activated complex is the point where all the old bonds have been broken. Then energy is released in order to form new bonds to form the product. Notice that more energy was absorbed and less energy was released. If you save more than you spend, you're going to have an overall increase in the amount of money, in this case, energy that you have. And that's an endothermic potential energy diagram. If you want to reverse the reaction, you start with the right side and you work your way to the left, which means this becomes the heat of reactants, this becomes the activation energy, this is still the activated complex, and this is now the heat of your products. So if you're asked for the activation energy of the reverse reaction, in this case, to reverse the reaction, we start at 80, we got to go to 140, which means 60 kilojoules would be the activation energy for the reverse reaction. Now, what if you added a catalyst or an inhibitor? Remember, catalysts will make a reaction go faster by removing steps. If you remove steps, you're still going to start in the same place. You're still going to end in the same place, but it will take you less energy to get there, which means that if you want to draw the potential energy diagram with a catalyst, you simply lower the activation energy. You start and end in the same place, only the peak comes down. And if you want to show what happens when you add an inhibitor, inhibitors slow a reaction down by adding steps. More steps will require more energy, which means it will require more energy to get to the activated complex. So catalysts will lower the activation energy, where inhibitors will raise the activation energy, though you will start and end exactly where you did before. Those are potential energy diagrams and where to put energy in a reaction. The next thing we're going to take a look at, well, I don't want to spoil it. So, let's see. According to my chart here, it's enthalpy and entropy. Ooh, we're going to make a real mess of things next time. Woohoo! So until then, as always, take care of yourselves, be well, be happy, be good, and bye!